Today we are looking at boundary conditions for the wave equation and how the same three condition types we saw before now describe something physical, like the motion of a vibrating string. Recall the wave equation itself. It states, the second derivative of u with respect to t equals c squared times the second derivative of u with respect to x. Here, u of x and t is the displacement of the string at position x and time t. Just like before, we still have three types of boundary condition: Dirichlet, Neumann, and periodic. But now each one describes a different physical end condition for the string. A Dirichlet condition fixes the displacement at an end. In words, u at that end, for all time, equals 0. Physically, this means the end is fixed and cannot move at all, like a guitar string tied down. Picture the string as a two-dimensional curve, height against position. At the fixed end, the curve is pinned to the axis, and any wave reaching it reflects back upside down, inverted. A Neumann condition fixes the slope at an end instead. In words, curly du by curly dx at that end equals 0. Physically, this means the end is free to move up and down, but the string cannot pass through that point, so the wave reflects there instead. Looking at the same curved view, the free end can slide vertically, but the tangent line stays flat there. A wave arriving at this end reflects back the same way up, not inverted. A periodic boundary condition ties the two ends of the domain together directly. In words, u at the left end equals u at the right end, and the slope matches too. This lets a wave leave one side and reappear on the other, which suits a circular or cylindrical domain. For the fuller visual breakdown, imagine bending the string into a loop instead of a straight line. There are no separate ends anymore, just one continuous shape, shown as a closed polygon outline rather than a flat strip, and never as a sector or pie slice. Now for the check step. Suppose both ends of the string have a Neumann condition, meaning both ends are free but cannot pass through. Send a wave toward one end. Because the slope must stay 0 there, the wave reflects back the same way up, in phase, not inverted. The same thing happens at the other end, and this repeats every time the wave reaches either boundary. This confirms the Neumann condition gives reflection in phase, rather than absorption or inversion, at both ends of the string.